Okay, so this do now here, it says label the following vectors using the nearest axis convention and counterclockwise from east. Okay, so we have two different vectors here that were given on a Cartesian plane. Our first vector is at an angle of 25 degrees with the horizontal. Okay, our second vector is an angle of 32 degrees with the horizontal. We want to label the direction in two different ways. Okay, so there's three correct ways to label each of these. Okay, you need to write down at least two. So let's give that a try. Okay, so what's one way in which we can label the angle in number one? Melissa.
25 north of the east.
Good, 25. I can hear you, you're good. Yep. 25 degrees north of east. Okay, because the actual vector, okay, the angle touches east. So of east comes second in our statement. So it's 25 degrees north of east, good. Or another way, read.
I said 25 degrees counterclockwise from east.
Exactly. So we start at the east axis and we move our pencil in the counterclockwise direction until we hit our vector, which ends up being exactly 25 degrees counterclockwise. Good. There's also a third way in which we could label this. What's another way in which we could label number one?
Could you say a clockwise measurement?
Okay, clockwise. You could do clockwise. Or what about east of north? We wanted the angle east of north.
65.
Okay, so we would take 90 and we would subtract 25.
Mm-hmm.
Good, and we get 65 degrees east of north. Okay, so three ways in which we can label this. In terms of the north axis, we'd have 65 degrees east of north. In terms of east, we'd have 25 degrees north of east. Okay, and counterclockwise, we'd have 25 degrees counterclockwise from east. Awesome. Good. What about this next one? Colin.
I said 328 degrees counterclockwise. It would be 360 minus 32, which would equal 328.
Good. So for number two, our counterclockwise angle, we'd take 360 and subtract 32 from it. We get 328. Oh, 228. No, 328. 328 degrees. Yes. Okay, good. And then what's another way in which we can label Madison?
32 degrees south of east.
32 degrees south of east. Good, because the vector makes an angle with east. Okay, and what would a third way? How else could we measure this? What if I wanted east of south instead? Colin?
58 degrees east of south.
So we'd subtract 32 from 90 and get 58 degrees east of south. Awesome. Okay. So on Thursday on your quiz, you'll have 4 questions. One of them is going to be determining direction, just like this do now. Okay, so this is something that you're going to want to look at when you're studying for the quiz. It seems like we have a good handle on this. Okay. Okay, so what we're going to talk about today is something that we call vector components. We're basically reverse engineering the process that we have been looking at. Okay, so we're going to take vectors and break them into their components. Okay, and remember that we're still talking about vector addition. So this is still under the umbrella of vector addition, so adding vectors. Okay, and the component form is most useful to us when we're studying motion. Okay, so when we look at projectile motion, we're going to use this mathematical procedure to take a look at the components of an object's velocity, to figure out how far away it lands, okay, how long it's in the air, etc. So before we get started here, let's just review quickly, what do we know about vector addition? What do we know so far about vector addition?
You can like rearrange them and they'll always equal the same thing.
Okay, we add our vectors tail to tip. No matter which way we arrange those vectors, we get the same sum. Awesome. If vectors are in the same direction, what do? We add them together. Okay, if they're in opposite directions, we subtract. What if they're perpendicular to each other? So we add them tail to tip and they're perpendicular. How do we find the sum?
Pythagorean theorem.
Okay, Pythagorean theorem. Good. And then how do you find the angle?
Trig.
Madison?
Inverse tangent.
Good. So we use inverse tangent, which is basically an inverse trig function, to find the angle or the direction of the vector. Great. So now, still under the umbrella of vector addition, now we are given R. So we're given the resultant, and we want to find the x and the y components. Okay, so we're reverse engineering this process. We're now given r and theta. We're given r and theta, the magnitude and the direction of the vector. We need to find the vector components. Okay, so to do that, the process looks pretty similar. Okay, let's pretend that r is 65 meters and theta let's go with 25. And theta is 25 degrees north of east. Okay, so we're given r and theta. We need to find the x and the y components. So the first thing we do is similar to our previous process. We draw the Cartesian plane, and on that plane, we draw our vector. So with our example of 65 meters, if the angle is 25 degrees north of east, that means that our vector is in the first quadrant. So that tells us which quadrant our vector's in. Of east tells us the angle is between east and the vector. So we figured out what quadrant it's in and we've drawn it. Our next step is we want to create a right triangle. That's always our goal. So we're going to take the tip of our vector and connect it to the x-axis. Okay, we can see that triangle. We're then going to label our x and our y components. So we're going to label the x and the y components. How do we know what is the y component? How do we know what the y component is? Madison?
It runs parallel with the y-axis.
Okay, so the y component is parallel to or on top of the y-axis. Okay, so the side that's parallel to the y-axis is the y component, which is r subscript y, which would mean the x component is either on or parallel to the x-axis. Great, so we labeled our vectors. Next thing we do is we use trig to find the x and the y legs of the triangle. The x and the y legs of the triangle. So, r, right, which we're told is 65, is our hypotenuse. We'll start with the x component. Okay, we know we need to use trig, so SOHCAHTOA. If I want the x component, or the adjacent leg, which trig function do we use? I want the adjacent leg and I have the hypotenuse and an angle. Which trig? Okay, cosine. So cosine of theta we know is adjacent over hypotenuse. Okay, so we're going to derive an equation that we'll use for every problem. So cosine of theta is adjacent over hypotenuse. So the cosine of the angle will be the r sub x, meaning the x component, over r, which is a magnitude. To get r by itself, r sub x by itself, we multiply both sides of the equation by the magnitude. So therefore, to find the x component, we take the magnitude of the vector and we multiply by the cosine of theta. So x is always cosine unless we're on an incline. Sine slides. So what this equation gives us is the x component of a vector, okay, and that's if it's measured with the x-axis. In all the examples we'll look at, theta will be measured with the x-axis when we're looking for vector components. Okay, so in every problem we look at, this equation will give us the x component. Technically, if theta is measured with the y, that equation will not work. Okay, but we will not look at any situations in which that happens. Okay, our shortcut equation for the y component, if we're looking for the opposite leg, we have the hypotenuse. So we're going to want to use the sine. So our second equation, we have sine of theta is equal to opposite over hypotenuse, which is technically the y component over the magnitude of the vector. We multiply both sides by r to get the y component by itself. We want an equation that gives us the y component. So we find that the y component is simply the magnitude of the vector times the sine of theta. So this equation works when we're finding the y component of a vector measured with the x-axis. Okay, and those two equations are going to be added to your note card under the words vector components. Okay, so we have r sub x is the cosine of theta times r sub y equals r times the sine of theta. Okay, and remember that r can be any vector. It can be velocity, acceleration, force. R is any vector. Okay, so please take a minute and add these to your note card. Okay, and we to continue on with the example that we looked at, we're now going to take those values of 65 meters at an angle of 25 degrees. And we're going to find, using those equations, the x and the y components. Okay, so if we're given a problem, it's going to look something like this. Suppose the person walks 65 meters, 25 degrees north of east. Okay, we already took the diagram, or have the diagram rather, from our procedure. We want to find the horizontal and the vertical components. Right, those words horizontal and vertical are just fancier words for x and y. So when you see those words components, you know to head to your note card and locate these two equations. Okay, so we're going to find the x component, we're going to take the vector, 65, and multiply by the cosine of 25. Your calculator must be in degree mode because theta is measured in degrees. So if your calculator is not in degree mode, you will get the wrong answer. Okay, on a TI 84 or 86, you go to mode. Okay, you'll see radian and degree. You want to make sure degree is selected. Okay, you'll do cosine of 25 times 65, and we should get 58.91 meters. So the x component is 58.91 meters. We can either label it as east or we could leave it as a positive value. So it will either be positive or east. Yes. Mm-hmm. Okay. So did we try the y component already? So talk me through it, Reed. Go ahead.
So I did ry equals 5 meters times sine angle 25, and I got 27.47.
Okay, so you had 65 meters times the sine of 25. You got 27.47 meters. Good. And our direction is either north or positive. North or positive. Good. Okay, so if you were, let's say that you're asking someone to meet you in the woods at this location, how would you describe to them how to find you? So to give them directions, what would you say?
I would say go 58.91 meters east and then
27.47 meters north.
Right. So that's why the components are useful. Because if we were actually physically giving directions, we'd start at the origin and move east 58.91 meters. And then we'd turn and move due north for 27.47 meters. That's how you describe to someone how to meet you. Good. So if we move our vector into a different quadrant, what do you think will change?
Just the directions.
Just the direction, right? So if we were to move this vector 65 meters and we were to go south of east, the only thing that would change is the direction in the x, right? So we move quadrants, only the direction will change. Good. All right, let's try one like that anyway. Okay, so we have, let's actually give this a try by ourselves. So it seems like we're starting to get this pretty quickly. So let's give this a try by ourselves. So we have a plane with a velocity of 63.5 meters per second at an angle of 32 degrees south of east. So what does that tell us? Madison?
That's going to be the fourth quadrant.
Okay, it'll be in the fourth quadrant because we're south of east. Okay, it tells us that R is 63.5. Okay, so our diagram's going to look like so. Okay, we're asked to find the plane's horizontal and vertical velocity components. Right, when we see those word components, we know we have to use the equations in terms of r sub x and r sub y.
It's the
Okay, so we take 63.5 times the cosine of theta. We get 53.85 meters per second east. Okay, and for the y component, we get 33.64 meters per second south. Or we could say negative. Okay, or we could say negative. Any questions here? Awesome. Okay, so what we're going to do now is we're going to break out and do the group practice activity, which is in Google Classroom.
Are you on the Django?